we start the next exercise, which is exercise number 1.2. In this, question number first is find the derivative of the functions y is equals to f of x using the derivative of the inverse function x is equals to f inverse y in the following. It means that here we have to find derivative of y with respect to x. It means that we have to find here dy by dx. But this dy by dx derivative of y we have to find using the derivative of the inverse function. X is equals to f inverse of y. It means that we have to find the derivative terms which x in terms of y. If the given function y is equals to f of x, then we have to first convert into inverse function. Hence, first we have to find inverse of the given function. That is, we can write x in terms of y. Hence, this function y is equals to root x, we can write x is equals to y square. If we differentiate the given function with respect to x, we get the derivative. With respect to y, we get the derivative of x dx upon dy is equals to, we have to find the derivative with respect to y is y square. The derivative of y square is 2y. Hence, dx upon dy is equals to 2y. But we have to find the derivative of y is equals to f of x. Means we have to find dy by dx. Therefore, we have dy upon dx is equals to 1 upon dx upon dy. We evaluate the value of dx upon dy is 1 upon 2y, which is a required derivative of y dy upon dx by using the derivative of inverse function, which is x in terms of y. And again, we can put this value of y, which is y is equals to root x. Hence, again we can write this dy upon dx is equals to 1 upon 2 under root x, which is a required derivative of y dy upon dx when y is equals to under root of x. Similarly, the next example is example number second. Y is equals to under root of 2 minus root x. Again here we have to find dy by dx, but by using the inverse of the derivative. Hence, we have to convert first inverse to the given function. It means that x in terms of y. If the given function is y is equals to under root of 2 minus root x, we can write it under root of 2 minus root x is equals to y. If we take square both sides, then we can write it 2 minus root x is equals to y square. Now, if this 2 would shift into right side, then we can write minus x root x is equals to y square minus 2. If we change the sign of every term, then we can write under root x is equals to y square, 2 minus y square. Now if we take the square both sides, then again we can write x is equals to 2 minus y square whole bracket square, which is the required inverse term x in terms of y. If we differentiate given function with respect to y, then we get dx upon dy is equals to derivative with respect to y of 2 minus y square whole bracket square. Now, by using the derivative of x raised to the power n, we can find it 2 into 2 minus y square into again the derivative of 2 minus y square by using chain rule. Again says 2 into 2 minus y square as it is. the derivative of 2 is 0 minus the derivative of y square is 2y. Now again we can write minus 2y, 2 into 2 minus y square into minus 2y. Minus 2y into 2 minus 4y into 2 minus y square. For we know that y is equals to under root of 2 minus under root x. Hence we can write dx upon dy is equals to 4y minus 2 minus y square. Equation number 1. But we have dy upon dx is equals to 1 upon dx upon dy. After substituting this value, we can write 1 upon minus 4y into 2 minus y square. If we substitute the value of y is under root of 2 minus root x, then we can write dy upon dx is equals to 1 upon minus 4 into under root of 2 minus root x into 2 minus under root of 2 minus root x, under root of 2 minus root x whole bracket square is 2 minus minus plus root x, which is the required derivative of y, dy upon dx. Here plus 2 minus 2 0, hence we can write again this minus sign numerator minus 1 upon 4 into root x into under root of 2 minus root x. Similarly, we can solve the next example number 3, y is equal to cube root of x minus 2. It is clear that we have to find dy by dx, but by using the derivative of inverse function of this function. If we have to find the inverse of this function, then we convert this term x in form of y cube or in terms of y. If the given terms is y is equals to cube root of x minus 2, we can write it y is equals to x minus 2 whole raised to the power 1 by 3. If we take cube both sides, we can write it x minus 2 is equals to y cube. If we shift this minus to right side, then we can write x is equals to y cube minus 2. If we differentiate the given function with respect to x, then we can write the derivative, with respect to y, then we can write the derivative of y dx upon dy. When the derivative of with respect to y is y cube minus 2. Now we can write dx upon dy is equals to derivative of y cube is 3y square minus the derivative of 2 is 0. Again we can write dx upon dy is equals to 3y square. But we have to find dy by dx, and we have dy upon dx is equals to 1 upon dx upon dy. And the value of dx upon dy is 3y square. We can write it 1 upon 3y square. If we resubstitute the value of y, then we can write 1 upon 3 into the value of y is cube root of x minus 2 whole bracket square, or we can write it 1 upon 3 into cube root of x minus 2 whole bracket square, which is a required derivative of y dy upon dx. Again, the next example is y is equals to log of 2x minus 1. If we have to find the derivative of y dy upon dx by using the derivative of inverse function, again we can find, first we have to find inverse of the given function, that is x in terms of y. If we have to find the x in terms of y, then we can write first log of 2x minus 1 is equals to y. If we transfer this log right side, then we can write 2x minus 1 is equals to e raised to the power y by using the definition of logarithm. Now minus 1 shift into right side, then we can write 2x is equals to e raised to the power y plus 1 or 1 plus e raised to the power y. This 2 is multiple. If we transfer it right side, then we can write x is equals to 1 by 2 into e raised to the power y plus 1. Now if we differentiate given function with respect to y, then we can write the derivative of x is dx upon dy. is equals to derivative of 1 by 2 is constant function e to the power y plus 1. Now 1 by 2 as it is, derivative of e to the power y is e to the power y. The derivative of 1 is 0. Hence we can write dx upon dy is equals to e raised to the power y upon 2. But we have to find the derivative of y with respect to x, dy upon dx. Then we have dy upon dx is equals to 1 upon dx upon dy. We know that the value of dx upon dy is e raised to the power y upon 2. Hence we can write it 1 upon e to the power y upon 2. Also we can write it 2 upon e to the power y. We know that the value of y is log of 2x minus 1. Hence we can write 2 upon e to the power log of 2x minus 1, which is the required derivative of y dy upon dx. Next one, example number 5 is y is equals to 2x plus 3. Similarly, we can find the derivative of y with respect to x is dy by dx by using the derivative of inverse of function x is equals to f inverse y. If the given function y in terms of x, then we have to find first its inverse, which is x in terms of y. Hence, first we have to find inverse of the given function x in terms of y is 2x plus 3 is equals to y. If we shift this 3 right side, then we can write 2x is equals to y plus 3 convert into minus 3. Hence, x is equals to 1 by 2 into y minus 3. If we differentiate a given function with respect to y, then we can write the derivative of y dx upon dy is equals to 1 by 2 constant function, and we can write the derivative of y is y minus 3. Hence, we can write dx upon dy is equals to 1 by 2 is a constant function. Derivative of y is 1 minus derivative of 3, which is constant function, is 0. Hence we can write the derivative of 1 by 2 into 1 is equals to 1 by 2, which is dx upon dy. But we have to find the derivative of y with respect to x. Hence we have dy upon dx is equals to 1 upon dx upon dy. We know that the value of dx upon dy is 1 by 2, hence we can write 1 upon 1 by 2. Again with this term we can write only 2, which is the required derivative of y dy upon dx. Example number 6 is y is equals to e to the power x minus 3. This function is y in terms of x. If we have to find the derivative of y with respect to x by using the derivative of inverse function, then again we first have find inverse of the given function. The given function is e to the power y is equals to e to the power x minus 3. We can write it e to the power x minus 3 is equals to y. If we shift this minus 3 right side, then we can write e to the power x is equals to y plus 3 or 3 plus y. We have to find the value of x in terms of y. Then this is shift right side, then we can write x is equals to log of y plus 3 by using the definition of logarithm. Now we differentiate given function with respect to y, then we can write dx upon dy is equals to derivative of y log of y plus 3. We know that the derivative of log x is 1 by x, hence we can write dx upon dy is equals to 1 upon y plus 3 into again a derivative of y plus 3 by using chain rule is equals to 1 upon y plus 3 as it is. Derivative of y with respect to y is 1, and the derivative of 3, which is constant function, is 0. Hence we can write the value of dx upon dy is equals to 1 upon y plus 3. But we have to find the derivative of y with respect to dy by dx. Hence we have dy upon dx is equals to 1 upon dx upon dy. We know that the value of dx upon dy is 1 by 3, means 1 upon y plus 3. If we shift this value y plus the numerator, then we can write y plus 3, means dy upon dx is equals to y plus 3. We know that the value of y is e to the power x minus 3. Hence, resubstitute the value of y e to the power x minus 3 plus 3 as it is. minus 3 plus 3 0, which is e to the power x plus 0. Therefore, dy upon dx is equals to e to the power x, which is required derivative of y with respect to x. Dy by dx is e to the power x by using the derivative of inverse function. So example number 6, 7 is y is equals to e to the power 2x minus 3. If we have to find the inverse of this function, then we can write it e raised to the power 2x minus 3 is equals to y. By using the definition of logarithm, if we know that if y is equals to log x, then we can write the value of x is equals to e raised to the power y. Hence, e raised to the power y, we can write it 2x minus 3 is equals to log y. Minus 3 shift into right side, then we can write 2x is equals to log y minus 3 converted to plus. 2 is multiple term, hence we can write x is equals to 1 by 2 into log of y plus 3. If we differentiate given function with respect to y, then we can find the derivative of x with respect to y. Dx upon dy is 1 by 2 is constant function. We have to find the derivative of log of y plus 3. We know that the derivative of log y with respect to y is 1 by y plus derivative of 3, which is constant function, is 0. Hence we can write it 1 upon 2y. But we have to find the derivative of y with respect to x, dy by dx. Here we find dx upon dy. We know that, or we have dy upon dx is equals to 1 upon dx upon dy. The value of dx upon dy is 1 upon 2y. We can write it 1 upon 2y. Also we can write it 2y. And we know that the value of y is e to the power 2x minus 3. Hence we can write 2 into e to the power 2x minus 3, which is the required derivative of y, dy upon dx. If we have to find the derivative of this function by using the derivative of inverse function, x is equal to inverse y, then we first find the inverse of this function. Given function is in form of log base 2 x by 2. We can write it log of base 2 x by 2 is equals to y, because we have to find the inverse function x in terms of y. Again we can write this log of x by 2 upon log 2 is equals to y by using the rules of log base n is equals to log m upon log n. If we shift this log to right side, then we can write log of x by 2 is equals to y log 2. Now, this log we take right side, then we can write this function x by 2 is equals to e raised to the power y log of 2. This 2 is divided by x, then we can write it x is equals to 2 into e to the power y log of 2. Now, if we differentiate given function with respect to y, then we can write dx upon dy is equals to 2 is constant function. We have to find the derivative of y, e to the power y log 2. We know that derivative of e to the power y is e to the power y log 2, and we find again the derivative of y log 2. Here log 2 is constant function. Here y log 2 is a constant function and the derivative of y is 1. We can write log of 2 into derivative with respect to y of y. Again this function we can write is 2 into e to the power log of 2 raised to the power y. Log 2 is a constant function and the derivative of y is 1. We know that a to the power log base a f of x is equals to f of x. Hence similarly we can write it 2 into e to the power log base e 2 raised to the power y is 2 raised to the power y. Log 2 into 1 is log of 2, which is the required derivative of y, dy upon dx. But we have to find the derivative of y with respect to x. Hence we have dy upon dx is equals to 1 upon dx upon dy. And the value of dx upon dy is 1 upon 2 into 2 raised to the power y into log 2. This can we write also 2 raised to the power 1, 2 raised to the power y is 1 upon 2 raised to the power y plus 1 into log 2. The value of y is log base 2 x by 2, hence we can write it 1 upon 2 raised to the power log base 2 x by 2 plus 1 into log of 2. Or this 2 log base 2 x by 2 we can write also into dy upon dx is equals to 1 upon 2 log base 2 of x by 2 into 2 log 2. 2 log base 2 x by 2 we can write it x by 2 into 2 log of 2. Here 2 is cancelled, hence we can write 1 upon x log of 2, which is a required derivative of y with respect to x. Dy by dx is 1 upon x log 2 when x y is equals to log base 2 of x by 2. In question number 2, we have to find a derivative of the inverse function of the following. It means that if the given function is y is equals to x square into e to the power x, means y in terms of x. If the derivative of the given function is dy by dx, then we have to find its derivative of its inverse function. It means that we have to find the derivative of x with respect to y. It is clear that we have to find dx upon dy. If the given function y is equals to x square into e to the power x, by using this function we can find the derivative of y with respect to x. It means that dy upon dx, and we have also required derivative dx upon dy is equals to 1 upon dy by dx. By substituting the value or derivative of dy by dx, we can evaluate a required derivative which is inverse function. Number first, y is equals to x square into e to the power x. If we differentiate a given function with respect to x, then the derivative of y is dy by dx. We can find the derivative of x square into e to the power x. This two function is in the form of u into v, and we know that the derivative of u into v is du into dv by dx plus v into du by dx. By applying this rule, we can write first function x square into derivative of e to the power x plus e to the power x into derivative of x square. We know that the derivative of e to the power x is e to the power x plus e to the power x into derivative of x square is 2x. If we take e to the power x common both terms, then we can write e to the power x into e to the power x, then we can write x plus 2, which is dy upon dx. But we have to find the derivative of inverse function, means we have to find dx upon dy. Here we have dx upon dy is equals to 1 upon dy upon dx. We know that the value of dy by dx is 1 upon x into e to the power x in bracket x plus 2, which is the required derivative of x with respect to y is 1 upon x into e to the power x plus 2. Again, similarly, we can find here dx upon dy by using this function. By using this function, we can find first derivative of y with respect to x dy by dx. If we differentiate given function with respect to x, then we can write the derivative of y dy upon dx. Here x into cos x multiple terms, then we can write it d upon dx x into cos x. If these two terms are in form of u into v, then we can write it x into derivative of cos x plus again cos x into derivative of x. We know that the derivative of cos x is minus sin x plus cos x into derivative of x is 1. Hence we can write it minus x sin x plus cos x, which is dy by dx. but we have to find the derivative of inverse function. Hence, we have dx upon dy is equals to 1 upon dy upon dx. By using this value dy upon dx, we can write it minus 1 upon x sin x plus cos x, which is the required derivative of the inverse function dx upon dy. Sorry, 1 minus x sin x plus cos x. Also, we can write it dx upon dy is equals to 1 upon cos x minus x sin x. Next example number 3 is y is equals to x into 7 raised to the power x. Similarly, we can find here dx upon dy by using y is equals to x into 7 raised to the power x. First, we differentiate a given function with respect to x. Derivative of y is dy by dx. We can find the derivative of x into 7 raised to the power x. These two terms are in multiple form, hence we can use derivative of u into v. We know that x into derivative of 7 raised to the power x plus 7 raised to the power x into derivative of x. First function into derivative of second function plus second function into derivative of first function. We know that the derivative of a to the power x is equal to a to the power x into log a. Hence, derivative of 7 raised to the power x is 7 raised to the power x into log 7 plus 7 raised to the power x as it is. The derivative of x is 1. Hence, we can write x into 7 raised to the power x log 7 plus 7 raised to the power x. If we take 7 raised to the power x common both terms, then we can write x log 7 plus 1, which is the value of dy by dx. But we have to find the value of dx upon dy, derivative of inverse function of y. Hence, we can write dx upon dy is equals to 1 upon dy by dx. We know that the value of dy by dx is 7 raised to the power x into x log 7 plus 1, which is the required derivative of x with respect to y, or which is the required derivative of inverse function of the y is equals to x into 7 raised to the power x. Similarly, we can solve this example. If we differentiate with respect to x, then we can write the derivative of y is dy by dx. We know that the derivative of x square plus log x, derivative of x square is 2x and the derivative of log x is 1 by x. Hence, we can write dy upon dx is by taking cross product 2x square plus 1 upon x. But we have to find the derivative of this inverse function. Then we have dx upon dy is equals to 1 upon dy by dx. 1 upon the value of dy by dx is 2x square plus 1 upon x. Hence, dx upon dy is x upon 2x square plus 1, which is the required derivative of the inverse function of y is equals to x square plus log of x. Similarly, the next example number 5 is also y is equals to x log x. If we differentiate with respect to x, then we get derivative of y with respect to x dy by dx. Here we use x into log x, means u into v. First function into derivative of log x plus again second function log x into derivative of x. We know that the derivative of x is 1 by x plus log of x into derivative of x is 1. Here x cancel. We can write 1 plus log x into 1 log x, which is a derivative of y with respect to x. But we have to find dx upon dy. Hence, we have dx upon dy is 1 upon dy by dx. The value of dy by dx is 1 upon 1 plus log x. This we can write dx upon dy is 1 upon 1 plus log x, which is the required derivative of the given function dy upon dx. Next, question number 3 is find the derivative of the inverse of the following function. and also find their value of the point indicated against them. This question is similar to question number 2. Here y is equals to x raised to the power 5 plus 2x cube plus 3x is a given function. If we differentiate given function with respect to x, then we become dy by dx. Here we have to find the inverse of the function. In this we have to find dx upon dy. By using dx upon dy is equals to 1 upon dy by dx, we can find the inverse of the derivative of the given function. For the value of x is equals to 1, we can evaluate required value of the functions. First, given that y is equals to x raised to the power 5 plus 2x cube plus 3x. Differentiate a given function with respect to x. The derivative of y is dy by dx. We can take a separate derivative of every term, which is derivative of x raised to the power 5, 2 is constant derivative of x cube plus 3 is constant derivative of x. Derivative of x raised to the power 5, by using the x raised to the power n, we can write 5 into x raised to the power 4 plus 2 into x cube derivative 3x square plus 3 into derivative of x is 1. Hence we can write dy by dx is equals to 5x raised to the power 4 plus 6x square plus 3. But we have to find the derivative of inverse function. Hence we can write dx upon dy is equals to 1 upon dy by dx. The value of dy by dx is 1 upon 5x raised to the power 4 plus 6x square plus 3. We have to find the inverse of the function at indicated point, means at x is equals to 1. Hence we have to find, for x is equals to 1, we can write dx upon dy at x is equals to 1 is equals to 1 upon, we replace the value of x by 1. Hence we can write it 5 into 1 raised to the power 4 plus 6 into 1 square plus 3. 1 upon 5 into 1, 5 plus 6 plus 3. 1 upon 6 plus 3, 9. 5 plus 9 is equals to 1 upon 14, which is a required value of the given function at indicated point. Again, example number 2. Y is equals to e to the power x plus 3x plus 2. We have to find dx upon dy at x is equals to 0. Dx upon dy means inverse of the given function. First we differentiate given function with respect to x. We get the derivative of y with respect to x, dy by dx. We have to find the derivative of e to the power x plus 3x plus 2. We can take a separate derivative of every terms. Here derivative of e to the power x is e to the power x plus 3 into derivative of x is 1 plus 2, which is constant function. Derivative of 2 is 0. After that we can write dy upon dx is equals to e to the power x plus 3. But we have to find the derivative of inverse function. Hence we have dx upon dy is equals to 1 upon dy by dx. 1 upon the value of dy by dx is e to the power x plus 3. Here, for the value of x is equals to 0, we can find dx upon dy at x is equals to 0 is equals to 1 upon e to the power 0 plus 3. We know that the value of e to the power 0 is 1 plus 3 is 1 by 4, which is the required value at the indicated point. Now again we have to find the derivative of inverse function, which is y is equals to 3x square plus 2 log of x cube at x is equals to 1. First we differentiate given function with respect to x. The derivative of y is dy by dx. 3 is constant function, we have to find the derivative of x square. 2 is constant derivative of log of x cube. This log of x cube we can write 3 log x. Hence 3 into derivative of x square is 2x plus 3 is constant, 2 into 3 is 6. We have to find the derivative of log x is 1 by x. It means that 3 into 2, 6x plus 6 by x. We can write it 6 into x plus 1 by x. Hence we can write again it 6 into x square plus 1 upon x. But we have to find the derivative of x with respect to y. Hence we have dx upon dy is equals to 1 upon dy by dx. The value of dy by dx is 1 upon 6 into x square plus 1 upon x. After that, this x we can shift in numerator. Hence dx upon dy is x upon 6 into x square plus 1. But we have to find derivative of x with respect to y at x is equals to 1. Hence, for x is equals to 1, we can write dx upon dy at x is equals to 1 is equals to 1 upon 6 into 1 square 1 plus 1. 1 upon 6 into 1 plus 1 2 is equals to 1 upon 12, which is the required value at the indicated point x is equals to 1. Here we have to find again dx upon dy at x is equals to 2. First we write the given function y is equals to sine of x minus 2 plus x square. If we differentiate a given function with respect to x, then we can write dy by dx is equals to derivative of sine of x minus 2 separate plus a derivative of x square. We know that the derivative of sine is cos, hence we can write the derivative of sine of x minus 2 is cos of x minus 2. We take again the derivative of x minus 2 plus the derivative of x square is 2x. The derivative of x is 1, minus 2 is 0. 1 into cos of x minus 2 is cos of x minus 2 as it is plus 2x. But we have to find the derivative of x with respect to y, then we have dx upon dy is equals to 1 upon dy upon dx. 1 upon the value of dy upon dx is cos of x minus 2 plus 2x. We have to find the derivative at x is equals to 2. Then dx upon dy at x is equals to 2 is 1 upon cos of 2 minus 2 plus 2 into 0. 1 upon cos 2 minus 2 is cos 0 plus 0. The value of cos 0 is 1. 1 plus 0, 1 by 1. Hence, the derivative of x with respect to y at x is equals to 2 is 1, which is the required value at indicated point. So here, x is equals to 2, it means that 2 into 2 is 4. 1 plus 4 is 5. The value of required value is 1 by 5. Next one is question number 4. If f of x is equals to x cube plus x minus 2, then find f inverse of dash means derivative of f inverse at x is equals to 0. First, we have to write given that f of x is equals to x cube plus x minus 2. If we differentiate given function with respect to x, then derivative of fx is f dash x. The derivative of x cube plus x minus 2, derivative of x cube is 3x square, plus the derivative of x is 1 and the derivative of minus 2 is 0. Hence we can write f dash of x is equals to 3x square plus 1. But we have to find f inverse of dash. Means we have f inverse of dash is equals to 1 upon f dash. F inverse of dash x is equals to f dash of x. We know that the value of f dash of x is 1 upon 3x square plus 1. If we put x is equals to 0, then we get f inverse of dash of 0 is equals to 1 upon 3 into 0 square plus 1. The value of 0 square is also 0. 1 upon 3 into 0 is 0 plus 1. Again we can write 1 upon 1, means the required value f inverse of dash of 0 is 1. Next question number 5 is, using the derivative we have to prove that tan inverse x plus cot inverse x is equals to pi by 2. If we prove this condition, tan inverse x plus cot inverse x is equals to pi by 2, then first we consider that the given function tan inverse x plus cot inverse x by f of x, let f of x is equals to tan inverse x plus cot inverse x. If we differentiate this function, we get the value of f of x is f dash of x. We know that derivative of tan inverse x plus a derivative of cot inverse x is tan inverse x is 1 upon 1 plus x square plus derivative of cot inverse is minus 1 upon 1 plus x square plus minus we get the value of 0, which is f dash of x. Therefore, we can say that f of x is constant. Let f of x is equals to c for any value of x. F of x must be c only, so connectively we can choose x is equals to 0. Therefore, if we substitute the value of x is equals to 0 in equation 1, then equation 1 become, we can write f of x is equals to tan inverse 0 plus cot inverse 0. We know that the value of tan 0 is 0, hence tan inverse 0 is 0, plus we know that the value of cot of pi by 2 is 0, hence the value of cot inverse pi by 2 is pi by 2, is equals to 0 plus pi by 2 is equals to pi by 2. Therefore, f of x is equals to tan inverse x plus cot inverse x, hence we can write tan inverse x plus cot inverse x is equals to pi by 2, which is the required proof of the given proof, hence proved. Again next one, sec inverse x plus cosec inverse x is equals to pi by 2. We have to prove that this sec inverse x plus cosec inverse x is equals to pi by 2. First we consider that f of x is equals to sec inverse x plus cosec inverse x. After that, if we differentiate given function with respect to x, then we can write the derivative of f of x is f dash of x. The derivative of sec inverse x is 1 upon x under root of x square minus 1 plus cosec inverse x is minus 1 upon x under root of x square minus 1. By adding both terms, we can get f dash of x is equals to 0, implies that we can say that f of x is also constant. Let f of x is equals to c for any value of x. F of x must c only, so connectively we can choose x is equals to 0. If we put this value of x is 0, then equation 1 become, we can write f of 0 or f of x is equals to sec inverse 0 plus cosec inverse 0. Here the sec inverse 0 is equals to pi by 2. Hence we can write f of x is equals to pi by 2. And we know that the f of x is equals to sec inverse x plus cosec inverse x is equals to pi by 2, hence proved.